We use computers every day, but have you ever stopped to think what's really going on under the hood? I mean, way, way down, deep inside the actual chip? Well, today we're basically digital archaeologists. We're going to go on an expedition to uncover the secret language of one of the most important chips ever made, the Intel 8086. The brain of the very first PC?
Okay, so it all kicks off with something like this. It looks a little like a secret code, doesn't it? This is what's called an assembly instruction. It's a super basic command. All MOV AX BX is telling the computer is, hey, see that piece of data in spot BX? Grab it and move it over to spot AX. That's it. It's kind of like taking a book off one shelf and putting it on another. Pretty straightforward, right?
But wait a second. Here's where it gets wild. How does a little piece of silicone, it's basically just sand and metal, right? How does that actually understand what we're telling it to do? How does a simple word like MOV turn into the millions of tiny electrical zaps that actually make stuff happen? Well, that is the big question we're digging into.
All right, so the answer, it's hidden. It's in this secret language that only the processor itself can speak. So let's pull back the curtain and unveil the world of microcode.
So, okay, what exactly is microcode? Well, the best way to think about it is like a recipe book that's hidden inside the CPU. That command we saw, MOV, that's like you walking into a bakery and just saying, I want a cake. The microcode, that's the actual recipe the baker, the computer hardware, has to follow. Get the flour, add the eggs, mix it all up, put it in the oven. It's what translates your big simple order into all the tiny fundamental steps the silicon can actually execute.
And this is a great way to see it all laid out. Step 1, you give the order, that assembly instruction. Step 2, the CPU finds the right recipe in its microcode. Step 3, that recipe breaks down into a whole bunch of teeny tiny little steps. We're talking microinstructions here. Things like flip this switch or open that gate. And all those little steps together, that's what gives you the final action. Honestly, this whole hidden translation thing, it's pretty much what makes all of modern computing even possible.
Okay, now that we get the basic idea of microcode, this is where the fun really starts. We can actually go digging for treasure. Because some incredibly smart people, these digital archaeologists, have managed to unearth and decode the original 8086 microcode. And what they found? Oh man, it's full of these quirky, super clever secrets that show you exactly how the engineers were thinking back then.
So get ready for this, because this one is a total mind bender. Inside the chip, there's a thing called the instruction pointer, or IP. Now, common sense tells you it should point to the very next instruction the computer's going to run, right? Makes sense? But on the 8086, it doesn't. Nope. To be more efficient, the chip is always trying to guess what's next, and it prefetches that data early. The IP is actually pointing to that future spot. So what does that mean? It means there's this little microinstruction called core, whose whole job is to constantly correct the pointer and pull it back to where it's supposed to be. It's like you're reading a book, but your eyes keep jumping a paragraph ahead, and you constantly have to force yourself to look back at the right sentence. Wild, right?
And believe me, it gets even weirder. The names for things on the inside don't match the names on the outside. For instance, there's a register, which is just a tiny, lightning-fast storage spot on the chip that every programmer knows as SI. But inside, in the microcode, they called it IJ. Why? Who knows? And then you've got two things that seem to be different registers, and an R, but they're literally the same physical component. This wasn't some screw-up, though. It's a clue. It tells us that this chip wasn't perfectly planned from day one. It evolved. The engineers were adding things, patching things, and making it work as they went along.
So you might be thinking, what's with all these quirks? Were the designers just messy? No way. Absolutely not. And that brings us to the really cool part. Figuring out how all these weird little oddities are actually signs of some truly brilliant engineering, all driven by the limitations they had back in the day.
Okay, check this out. This is a perfect example of what I'm talking about. The chip literally uses the exact same ID number for two completely different things. It all just depends on the context. So if that ID is the source of some data, it refers to sigma, which is just the result from a math calculation. But if that same ID is the destination for data, it refers to a totally different temporary storage spot. Now, why on earth would they do that? Simple, to save space. Every little bit of silicon was precious. This is just an incredibly efficient, really clever way to squeeze more power out of less physical hardware.
And this whole obsession with efficiency, it leads to what might be the most amazing discovery of all. Just look at this number, 4. That's it, just the number 4. Because that little number is the key to an absolute stroke of genius. Think about this. How is it even possible that just 4 tiny micro instructions can run almost all of the math on this chip? I'm talking addition, subtraction, you name it. Basically everything the 8086 CPU can do, handled by just 4 little routines. The answer is one single beautiful micro-operation, ZXI. You can think of ZXI as the Swiss Army knife of the 8086. See, instead of writing out separate microcode for adding and then more for subtracting and so on, the engineers built this one tool, ZXI. It's smart. It looks at the command the programmer originally wrote and just changes what it does based on that command. It's the ultimate multitasker, and it does all the heavy lifting for the chip's math, which saved a ton of space.
And this quote just nails it perfectly. The amount of reuse here is elegant and very 1978 Intel. This wasn't just being clever for the sake of it. This was a signature move for the time. It was a whole design philosophy that was born out of necessity, out of constraints, and the result was just pure engineering elegance.
So, at this point, you might be asking, okay, this is cool history, but why should I care about some 40-year-old computer chip? Well, it's because this ghost in the machine, this whole hidden world of microcode, teaches us these fundamental lessons that are still super relevant to the technology we all use today.
So, what are the big things to take away from all this? First, abstraction is king. This whole idea of building really complex systems on top of simpler hidden layers, that's the bedrock of all modern tech. You don't need to know about microcode to send a text, right? And that's the whole point. Second, engineering is totally a creative process. The crazy limitations they had back in 1978, they didn't stop them. They forced them to come up with these brilliant, elegant solutions. It really proves that constraints can spark amazing innovation. And finally, this isn't just dead history. The design DNA of that old 8086, that whole philosophy of reuse and efficiency, it's still alive and kicking inside the processors we use every single day.
And that just leaves us with one final thought to chew on. We've uncovered the secrets of the 8086, its clever hacks and its elegant design. But what about the chips that are sitting in your phone right now, or in your laptop, or your car? What incredible, clever secrets are hiding deep inside the technology that's powering our world today? Kind of makes you wonder, doesn't it?